everyone, welcome back to my channel. Now that we understand the objective of backpropagation, let us begin with mathematical derivation. To make the derivation simple, instead of considering a large neural network with many neurons in each layer, let us start with a very thin neural network containing only one neuron in each layer. This simplified network has an input neuron, two hidden neurons, and one output neuron. The weights connecting these neurons are represented by W111, W211, and WL11. The network performs the forward pass and finally produces a prediction denoted by Y. Once the prediction is obtained, we calculate the loss function presented by L theta, which measures the difference between the predicted output and the actual target. Now our objective is to compute the following quantity: the partial derivative of the loss function with respect to the weight W111. But what does this derivative actually mean? It tells us how sensitive the loss function is to a small change in the weight W111. In other words, if we slightly increase or decrease this weight, how much will the loss change? If changing the weight causes a large change in the loss, then that weight is very important and should be updated carefully. On the other hand, if the loss changes only a little, then only a small update is required. Therefore, our entire goal in backpropagation is to compute these gradients for every weight and every bias in the network. Once these gradients are available, gradient descent can update the parameters and gradually minimize the loss. The challenge in the weight W11 is far away from the output layer. Its effect on the loss is indirect because the information passes through several intermediate neurons. So how do we compute this derivative efficiently? The answer lies in the chain rule of calculus, which is the mathematical foundation of the backpropagation algorithm. Now we are ready to compute the gradient of loss function with respect to the weight W111. Recall that this weight is located near the input layer, whereas the loss function is computed at the output layer. This means that the weight does not influence loss directly. Instead, its influence passes through several intermediate computations inside the network. Because of this indirect relationship, we cannot compute the derivative in a single step. To resolve this problem, we use one of the most powerful concepts in calculus called the chain rule. The chain rule states that if one quantity depends on another, which in turn depends on another, then the overall derivative is obtained by multiplying the derivatives along the dependency path. In our neural network, the dependency path starts from the weight W111. This weight affects the first pre-activation value. The pre-activation value affects the first activation. The activation influences the next layer. The process continues through every hidden layer until it finally affects the output prediction. And ultimately, the prediction determines the loss. Therefore, instead of computing one complicated derivative, we break it into several smaller derivatives. Each derivative measures how one variable influences the next variable in the network. By multiplying all these small derivatives together, we obtain the overall gradient of the loss with respect to the weight W111. This is exactly what the long chain rule expression shown on the slide represents. Although it looks lengthy, it simply follows the path from the loss function all the way back to the weight. To make the notation simpler, we often combine all the intermediate derivatives into a single term. This allows us to write the gradient in a much shorter and cleaner form. Notice that the gradient can now be viewed as the effect of the loss on the hidden neuron output multiplied by the effect of that hidden neuron output on the weight. This simplification makes the mathematical derivation much easier while preserving exactly the same meaning. Finally, remember that the prediction produced by the network depends on the output layer activation, which itself depends on all previous layers. That is why the chain rule becomes the foundation of the backpropagation algorithm. Without chain rule, it would be practically impossible to compute gradients efficiently in deep neural networks. Finally, let us interpret this in terms of neural network. Each bar is created by two neurons, one neuron with positive weight, one neuron with negative weight. These outputs are combined in the next layer. By using many such neuron pair, we can create many bars. And by adding all these bars, the network approximates an arbitrary function. This is the intuition behind why neural networks are universal function approximators. To summarize, a neural network approximates any arbitrary function by creating local feature using hidden neurons, combining them through weighted summation, and refining the approximation as the number of neurons increases.